Okay, let's talk about functions. Functions are a big thing in math, not just algebra. And so what we have right here is something that, well, it's just kind of a different way of presenting a function. It's not the way that you will typically see it in this class, not at all, but it is a good way to start getting your feet wet, okay? So something is, a relation is a function if everything in the domain is used at most one time. So nothing in the domain is used repeatedly. So for example, lake is associated with -7 and nothing else. Okay. Chair is associated with -7 and nothing else. So lake and chair, they are not used more than once, nor is cloud, door, or rock. Therefore, it is a function. All right. So how about relation number 2? Well, 3 is used just once and -7 is used just once. So it looks like we've got a function. 8 is used just once, but 0 is used, is associated with the number 8 in the range and the number -5 in the range. So not a function. Okay, that is how that works. Now, there's actually a 4-part problem. So let's check out the rest of it. I need to zoom out a little. Yeah, that's enough right there. Okay, so what about this guy here? Is that a function? Well, is anything in the domain used more than once? Well, we got B, S, Z, H. None of them were used more than once in the domain as an X value. Now, H was used more than once in the range, and so is Z, but when I am determining if something is a function, I don't care about the range. I'm only looking at the domain. So this one is a function. How about number 4? -5, 2, -8, -9. None of those X values got used more than once. So yes, this one is also a function. So number 2 is the only one that was not a function on this problem. Okay, so now we're still determining if something is a function, but for this one, they give us the graph of the relation and say, hey, is it a function? Yes or no? Well, you can do what we did in the last topic just a second ago, or you can use the visual equivalent of that last topic, in what's called the vertical line test. So here's how it works. If you can draw a vertical line that hits the relation more than once, then it is not a function. Okay, because those 2 points that I designated, they have the exact same X value. That X value is getting used more than once. That domain value is being used more than once, therefore not a function. On graph number 2, doesn't matter where you put the vertical line, you will never hit, no single vertical line will hit the graph more than once, therefore it is a function. How about graph number 4? Well, that's definitely not a function. I can find a single vertical line that hits it more than once. So no, not a function. How about graph number 1? Turns out this is a function. I mean, yeah, that vertical line hits it just once, and so does that. But what about that vertical line? Well, it hits the graph right there, yeah, but this is an open circle, and so it's not actually hitting the graph. So that is a function. How about graph number 3? Nope. If I draw this vertical line right here, it hits the graph more than once. In fact, 3 times. That's out of bounds. And the last graph, number 6, well, that only hits it once, and once. Okay, so every vertical line I draw is going to hit the graph at most one time. So it is a function, and that is how those are done. Once you get the hang of these kinds of problems, it's, well, they're really nice because they get to be fast and easy. Okay, so now what do we have? Well, we've got this is, we've got this thing right here. This is what a function will usually look like that when you work with one. You'll see g of x or f of x or h of x, something like that. And then you'll see this over here. Now, this is essentially the same thing as y equals 5x minus 4. So your question is, hey, I like y. Why did we replace it with g of x or f of x? Well, it turns out that for a lot of things in algebra and mathematics generally, that this notation ends up being easier to read and work with. Okay, you'll just have to take my word for it for now. Okay, so what are we doing right here? Well, they're saying, hey, we give you some x values, find the corresponding y values. So, when x is -4, I could just plug that in for x right there and then solve for y. Well, it works basically the same way. If you look at it like this, then we would be looking for what's called g of -4, because for the moment, x is -4. So I replace the x with -4. And if I replace it on the left side of the equation with -4, I need to do it to the right as well. So I'll replace that x with -4, and I get -24. So the point, -4, -24, is on the graph of this function. If we were to graph it, well, this point would be on there. We could just go graph it right now. I mean, why not? So I could go to y equals, clear out my old stuff, and type in 5x minus 4 and see what that graph looks like. There it is. It's that blue line. Hallelujah. Okay. Let's see. Okay, so how about the next one? And let's, so now we're looking for g of -3. So 5 times -3 minus 4 is -19. So if we were to graph this thing, the point -3, -19 would be on that line, just like that line that I did on the calculator a moment ago. Cool. Let's do one more. How about g of 2? Okay. So I do this. So I know that 2, 6 is a point on the graph. In fact, now that one is closer to the origin, so we'll see that more easily if we look at it on the calculator. Let's take a look. So if I use my arrow buttons, I go, whoops. Okay, so I'm looking down here, looking for when I have about 2 for my x value. That's good. And if I go up to the line, it should be about 6. Again, it's not perfectly accurate, but that's okay for this example. Okay, so and I'm on the line, and yeah, so when x is about 2, y is about 6. So, suggesting that 2, 6 is a point on the line. Okay. And that's all you do. Okay, so they say, go find f of 3, that's a cursive f, lowercase f, which means go to the f function and plug 3 in for x. All right, so I'll do it. And then I simplify, and I get 3 squared is 9. And then -27 minus 2 is -29. And that lets me know that the point 3, -29, is a point on the graph of this function. Okay. What about g of -7? Okay, so that says go to the g function and plug in -7. And so I can conclude that the point -7, -31 is a point on the graph of g of x, of that function, if you plug it in, or y equals 4x minus 3. Okay, so Leela rented a truck for 1 day. There was a base fee of $8.75, so she has to pay that automatically. Not much. And there was an additional rental or charge of 8 cents for every mile. So C of x represents the total cost, C for cost. And x is just however many miles were driven. So the cost is $8.75 plus 8 cents for each mile driven, where x represents miles driven. Okay, so they say, well, what's the total rental cost if Leela drove 30 miles? So is 30 going to be plugged in? Is that going to replace C of x, or is it just going to replace x? Well, it's 30 is measured in miles, not dollars. Okay, well, C of x, that's our cost. That's dollars. This is, and 30 is not, it's not $30, it's 30 miles. But x, that's a measurement of miles. So this is an x number. So we replace the x's with 30. And you're going to get a lot of practice with this, because functions are something that are just not going to go away as long as you're taking math. Okay. Okay, and then we get $2.40 for the miles that she drove. And then if we add to that the $8.75 for the base rental, then we get $11.15 for renting the truck. And that's what you do on these problems. They give you a number, you plug it in for x. Okay, but you need to think about why you're plugging it in for x, and don't just do it automatically, but think about it, because you need to understand functions. All right, Aldo wants to save $600 to buy a TV. Cool. He saves $19 every week. The amount A in dollars, A for amount, that he still needs after W weeks is given by the following function. Okay, so you have one thing you have to do in word problems is make sure you understand what the variables mean. W stands for the number of weeks that have already transpired. Okay, so after W weeks of saving. So W is how many weeks he has already been saving, or she. I'm guessing he, I don't know. And then A, or A of W, that stands for the amount of money that he still needs to earn. Okay, not how much money he has earned. The amount of money he has earned, that's $19 multiplied by how many weeks he's been saving. Okay, but how much money he still has to go? Well, that's how much money he needed at the beginning minus how much he has saved. So 600 minus 19W. All right, so let's check out these questions. How much money does Aldo still need after 7 weeks? Now 7, that is measured in weeks, not dollars. A of W is dollars. This isn't $7. It's 7 weeks. Well, W, that's our number of weeks. So 7 must be a W number. So we plug it in for W. We say, all right, well, A of 7 is 600 minus 19 times 7. And this will tell us how much money he still needs to save. And he still needs to save $467. Yeah, he's getting there. He's got $133 saved already. All right, cool. Well, what about if Aldo still needs $258, how many weeks has he been saving? So 258, that's not number of weeks. That's not a W number. That's dollars. And A is what's measured in dollars. So Aldo still needs 258. So that is our value for A of W. So all of this is going to get replaced with 258. Okay, so it'll be 258 equals 600 minus 19W. And that makes sense. Okay, so let's subtract 600 from both sides. Okay. And we get 342 negative is negative 19W. And when we divide both sides by negative 19, we end up with a positive 18. 18 what? Well, W is measured in weeks, so 18 weeks. Does the answer seem reasonable? Yeah, it's not negative. It's not, like 500 weeks or, something that would just be totally unrealistic. But yeah, that's kind of how it goes. So in this topic, you're not only going to be plugging in a number for the independent variable x, or in this case w, but also for the name of the function, which in this case was a of w, where we plugged in the 258.